Hey, okay, so today we're going to learn about higher order derivatives, which just means taking the second derivative, third derivative, so on and so forth. So for the first do now here, I want you to find the derivative of this function right here. Then find the derivative to your answer to number 1. Find the derivative to your answer to number 2. Try to make a generalization. Do the same thing with this second function here, okay? Then try to make a generalization. So pause the video, find all these derivatives by hand, and then we're going to meet back here in a second. Hello, welcome back. So maybe you will have seen when you did the first one, you were taking the derivative of a polynomial over and over and over again, right? So we started with a quadratic. We took the derivative and we ended up getting a linear function. We took the derivative of a linear function, and since the slope of this line is constant throughout, the derivative of a linear function is going to be just a plain old constant. And then if we took the derivative of that constant, we would end up with a 0. So the general trend that we can comment on here is what happens when you keep differentiating a polynomial. You eventually get to 0. Right? A power keeps peeling off every time until you end up with no powers. Let's look at the function below. It's a little tricky. It's a square root and a cube root, right? So let's see what happens when we start taking the derivative of roots a bunch of times. Okay, so the first function was this red one here. Then we took the derivative of that guy, and we ended up with this brown one here. And then we took the derivative of that guy, we ended up with this blue one here, okay? So as you can see, you keep taking the derivative of a root, and it just keeps getting more and more complicated, and it never approaches 0 like the polynomial does, okay? So that's just kind of, you keep getting new roots for functions. Never approach 0 like the polynomials do, okay? So that's just a cool distinction. Let's talk about a second derivative. So as you differentiate a function to find its derivative, you can also differentiate a derivative. That means take the derivative of the first derivative. And that gives you the second derivative. Let's look at this notation here, okay? So you take the first derivative, right? And you would get the first derivative is dy dx. So the second derivative looks like the derivative of dy dx, which would end up being d squared y over dx squared. You could also see two little prime tick marks up there, or you can see two tick marks after the y. So the third derivative would have similar notation. You take the derivative of the second derivative, and you end up with d to the third y over dx cubed, and that would be equal to f with 3 tick marks and y with 3 tick marks, okay? And then the nth derivative, aka anything past 3, instead of using tick marks, you're just going to have the derivative number here. So like the fourth derivative would be like d4y over dx to the fourth, or it would look like this. Okay, so they don't use the tick marks anymore past 4, then they just like write it y to the fourth, f to the fourth of x. Okay, so that's just saying the fourth derivative. That's notation. Now let's talk about what taking derivatives of derivatives is actually telling us, right? Let's root this in your personal favorite, physics. Woo! Okay. So let's say that this is the position function modeling your car's position over time, right? If I took the derivative of that curve, I would get the slope along the curve at any point, right? I would get the velocity of the car at any point over time. And it looks like that velocity is a linear function. And then I take the derivative of a linear function, and what do I always end up with? A constant, right? So basically, this is measuring the slope of the original curve. So this second derivative here would end up measuring the slope of the slope, which makes perfect sense when you think about it in terms of velocity and acceleration, right? How much is your velocity speeding up or slowing down? That's what acceleration is telling us, okay? And since acceleration is located down here below the x-axis, we would see that this guy is has a negative acceleration, okay? All right, so we don't need to get too vested in the physics of this. We're going to learn about that in the next unit. But this kind of is a really nice encapsulation of why we would ever want to take a second derivative or a third derivative, okay? So it says if derivatives can tell you the slope of a curve at a point, then the second derivative tells you the slope of the slope. How much are you speeding up? How much are you slowing down? Let's practice calculating some of these. So it says find the second derivative of the functions below. So in number 1, I want to use the power rule. However, I have a little fraction over here. So I'm going to rewrite 1 in a more usable form, and then I will take the derivative using the power rule. The directions say to take the second derivative. So I'm going to take the first derivative, then I'm going to take the second derivative. All right. So I'm going to take the first derivative. So that's going to be 21 divided by 3, which is 7x squared minus 4x plus 3x to the negative second. Let's take the second derivative. Notice how we didn't convert it back into rationals and everything until after we took the derivative again. So now we have 14x minus 4 minus 6x to the negative third. So then I would convert that to 14x minus 4 minus 6 over x